the next course to be released is our differential equations course,
Hmm.
which is well underway. And why don't you let's just talk a little bit where we're at, what it is. I mean, whatever, however you want to describe it.
So yeah, so we're well underway with the differential equations course. I have kind of gone public and said that I'm hoping to release it before Christmas, because last year, like, we managed to release, like, last year, probability and statistics on Christmas Eve, and that was what I wanted to do. It's like that'd be a great thing to be able to kind of maintain. I'm slightly regretting actually saying that now, although I'm still aiming for it. The thing I've realized is that a lot of these stuff on, so we've actually had quite a lot of differential equation stuff like in the background. So if you go through the Math Academy system and you complete all of our high level courses like linear algebra, methods of proof, multivariable calculus, discrete math, and probability and statistics. If you finish those, you start getting like what we call Easter egg topics, which are topics in the system, but they're kind of like not in any particular course, which is available to the public. And the reason those topics exist is because is to help out with the high school program. Like years ago, you had all these kids finishing calculus at like 8th grade or whatever, and it's like, well, we need stuff for them to do. So we went in and we create a whole bunch of abstract algebra topics and differential equations, and and obviously eventually finished up all the multivariable calc and linear algebra. So eventually got them to piece into these actual proper courses. But I'm looking back at some of this original content, as there's so much we've learned about how content should be created that we didn't really know back then. So just to give you kind of one kind of example, so we got a probability and statistics course, and within that topic, I think the course has gone down really well. But there's one or two topics on moment generating functions where basically the way the questions have been designed, it's very easy for the student to kind of like infer what the correct answer is going to be, because it's like there's this particular pattern that makes it very, very easy to go, oh yeah, that's the correct answer, that's the correct, see one or two, and then they can just, even if they don't know what the hell's going on, they can just kind of get through it. And even the most well-intentioned student who wants to know it, they might be tired, whatever, and they're just clicking and they're spotting the pattern and just kind of getting through. And a few people complained about this. Said, yeah, this is really silly, blah, blah, blah. So we've got a particular topic. We've got a big area of the differential equations course is going to be Laplace transforms. Now, Laplace transforms are basically the same as moment generating functions in a slightly different context. And it's like, okay, I've got to make sure we don't make that mistake again, So I've gone back. Now, Laplace transform is actually one of these Easter egg topics. So I've gone back and looked at it and gone, oh yeah, of course, this was created like 5-6 years ago. Of course, it's got the same problem as that moment generating function topic. So what I need, so basically, those topics almost have to be like completely rewritten. What we're going to do this time is, rather than just like multiple choice, whatever, is almost use dynamic select questions to kind of like walk the student through the calculation. So they've really got to like think at each step. So there's quite a lot of work to do in terms of fixing prior, like, not ills exactly, but to improve the content based on what we know is good practice right now. And of course, when we did the high school program stuff, there were certain topics that we just were I guess were missed, shifting theorems and things like that. So yeah, just going and backfilling a whole bunch of stuff. So there's a few other areas as well. Like one of the earlier topics is going to be like first order differential equations. Well, I've noticed a lot of resources actually kind of dive into like the method of integrating factors straight away, which you can understand why they do it, but actually they should go back and sort of do linearity first, really explore it, because there's some missing scaffold in there which could be exploited. But to cut a long story short, there's a lot of backtracking and putting things as they should be to create a kind of commercially viable course. So Christmas is definitely possible, but it's a lot of work.
So like one thing that I always, when I would say, hey, Alex, this is what I think we need out of this course is, it needs to be at the level of what you would see at Harvard or MIT or Stanford or whatever, right? Mm-hmm. So You don't want someone to say, well, that thing at Math Academy. I mean, it's not bad. I mean, it's just kind of cute, but I mean, that's not what we do at Berkeley or Harvard or something, right? You
Yeah.
want to be like, yeah, man, like it's legit, right? And so, one thing that I asked you to do when we first created we created our very first um, university level courses, linear algebra and multivariables, like go look, what can you find? What are they doing? If you can see any published final exams or syllabi from these elite institutions, along with the most popular, most well-respected textbooks that are used at those institutions, what are they? What are they covering? Like, what's the superset of the commonality, right? There's always some. Justin would always point this out. There's always some really weird, idiosyncratic topic that some professor covers because maybe it's related to their area of research and they just find it neat, but nobody else will talk about it, and everything's kind of weird. But if you shave those off and you're like, okay, they covered this at MIT and this at Caltech and this at Stanford and this at Chicago and this at Duke and this at, and you go all that and you go, okay, what is that? Because you don't want to go, well, they don't cover this and they cover this at MIT. It's like, well, they didn't cover that at Stanford and they didn't cover that at Oxford. But you look pretty broad, far and wide to just make sure that we're covering all this stuff, right? I mean, just talk a little bit about that because I
Yeah.
find that interesting.
Yeah. So, yes, in terms of what a differential equations course should look like, there does seem to be like a sort of a general consensus among the top universities, like US universities. So yeah, so we sampled, I think, like 8 to 10 of the top universities in the US and came up with a list of topics which they all seem to cover, plus some, plus a handful which some of them cover, some of them don't. And it was from there that we kind of really came up with our first kind of course outline. Now, we are somewhat constrained in the sense that, it needs to be a semester long course. So, maximum 200 topics for a course like this. So that is kind of a constraint. But I think that the differential equations course we have planned is going to cover everything that you see at most of these universities. You always get people online sort of asking, hey, you're going to have PDEs, you're going to have signal processing and this and that. It's like, well, they're typically covered in like later courses. We're just doing a extremely comprehensive differential equations course, but it is an introduction to differential equations. It's not going to be, sort of pulling in things from that you wouldn't normally expect to see.
Yeah, it's the same kind of scope creep that we saw in machine learning or even in the linear algebra, right? Like people often confuse like Axler's linear algebra done right. No, that's a second linear algebra course. You wouldn't see that in a first semester linear algebra course. So it's kind of the same situation with differential equations. It sounds like where we have to draw the line somewhere, right? We can't just have it expand out indefinitely until you're doing like research on Navier-Stokes as your final topic. Like, no, we need to keep the scope down.
Yeah.
I mean, I think it's important, as we've talked about this for years, is to have apples to apples comparisons with what we're doing and what is done at a comparable level. So it's like our Algebra 1 course can be, it's a year long, it's a 9-month course, right? Because that's what's done in schools. When we think of algebra, what is Algebra 1? Now, we could be more comprehensive because you look at different textbooks and they go a little deeper on this or a little deeper on that. And because we have an extremely efficient pedagogy and learning algorithms, that we can do more, but nevertheless, it still has to be a year-long course. Now, for university courses, they are a semester or quarter-long course. Now, for people who aren't familiar, in the U.S., course, probably 3/4, probably maybe more, maybe 80% of universities run a semester system. So the year is divided into two. So it would be a half-year course, and you would take, 4 to 5 courses. In some schools where I went to University of Chicago, it was quarter based. So you had a fall, winter, and spring quarters, and so you would only take 3 or 4 courses. So you would do more in less time. You have fewer courses that would cover a little more ground. But regardless, they're pretty much the same it's pretty much the same amount of material. So our university courses need to fit in that framework so they can compare it and go, okay, as a semester, quarter long course, math course, how does this stack up to what's going on? If you do it like a year-long course, people are like, well, is this like and everybody gets confused. And so we always say, like, we can reinvent a lot, but we do not exist in a vacuum. We exist in a world where things are done a certain way and people have certain understandings and expectations. And if you drift too far off that, then people just do not know how to think about what your product is or what you're doing. And it just becomes so much friction in crossing that it's just, it caused the product to fail. So we need to be, okay, people go, oh, so it's Calc 1. Calc 1 is a semester quarter-long course. Calc 2, I get it. Linear algebra, so we have to kind of do that. So I think you're right. Like, put a cap on it. It's ordinary differential equations. It's going to be a superset of a bunch of stuff. So if you go to one of these courses, you won't be able to go, well, we don't cover that. It's like, hell no, we do cover that. Cover all that. But we're not going to go crazy, and then we can do the partial differential equations course or something like that as a second course later. I mean, I think we have our sort of goal is to get the lower courses first. So I think differential equations is sort of like a legitimate sophomore or junior level course, depending if you're applied math, you might take that your sophomore year. I mean, you would take, the standard is you take Calc 1 and Calc 2 as your freshman year. You would take linear algebra, multivariable calculus your sophomore year, maybe differential equations, or maybe your differential equation would be a junior year. Now, I was pure math, so I never even took differential equation. Mine was real analysis, abstract algebra, and stuff. So, but if we get this down, if we get differential equations down, I feel like we've covered most of the lower introductory level, sophomore, junior level stuff. Now, pure math, of course, we would have to do real analysis. I'd cover that. So, I mean, Alex. Go on, Alex. I mean, Justin. Go on. Say.
Oh, I was just gonna say, yeah. This is like the last course in the core engineering sequence,
right,
for an undergrad. I think that's like the special part about it. But yeah,
a lot more people who need to know differential equations and need to know real analysis.
Yes.
So it's a better or abstract algebra. But then after this, so the goal for differential equations is we'll have it done by the new year. And then after that, it's on to, I mean, obviously we're going to try and roll out machine learning, but that's not really a content thing. That's more a technology thing. At this point, the content is basically done. It's abstract algebra.
Mm-hmm.
Alex, is that what you're thinking?
Yeah, I think we can get the ball rolling on abstract algebra, but we've. I mean, maybe this is a conversation for another day. But sort of upgrading the kind of like the proof infrastructure, and probably rolling that out into something like methods of proof first, and then but working on abstract algebra, because not all abstract algebra is going to be like require like free form proofs. There's still a lot of stuff we need to do on the content end. So, but yeah, broadly speaking, get some proof infrastructure in place. Then methods of proof, update that to have the free form proofs, then onto abstract algebra, and then real analysis.
Yeah. Okay. So yeah, we won't go into detail on that. But so differential equations course, how are you feeling about it? I mean, is it as a course?
Yeah, I feel good. I mean, it's yeah. I mean, I think that we are kind of like. I'm excited about it for sure. Yeah. It's because we've got all this existing content already, and we're kind of like filling in the gaps. It's kind of like it's a little bit difficult to see the wood for the trees in some sense at the moment. But I think it's going to be a great course. And one thing is as well I was going to say is that there are opportunities to enhance this course, like some of the like the numerical methods. We've learned a lot about how to deal with like highly numerical work, sort of like basically doing algorithms, but by hand.
Range kata and things like that.
Stuff like that. Yeah. So we in the calculus courses, we've got something called Euler's methods, which took a few iterations to get right. But now that we've got it right and the pass rates for that are really high, it's like you just need to carry that same methodology through to the differential equations course. So we know we know it should work. I mean, it's the same thing, but just sort of it's slightly more complicated. But then once we have the coding infrastructure in place, we can have like coding courses. So students can kind of complete the loop. It's like they do it by hand, they get proficient, and then we give them like a cool coding project where they actually have to, predict something about the weather using like the Runge-Kutta method or something like that, which I think would be really cool and help to kind of square that off.
Yeah, that'd be awesome because differential equations opens up so much surface area to cool modeling projects. I mean, I remember back when I was really getting interested in applied math, that was the thing that did it for me. Differential equations, modeling everything, biology, weather, whatever. So yeah, I'm sure we could get a ton of cool projects out of that.
Yeah, so there's going to be a lot of potential. Once the course is done, there's a lot of potential there in like a V2 where we do some more projects that involve coding and modeling and things. So yeah, that's going to be really exciting.
Yeah, I guess it's like the coding thing is interesting because we could have versions of courses that require coding or don't. It'd be interesting to have like you could do differential equations, you could do linear algebra, you could do all these things. You could have a code which just has a ton of coding projects with or without coding. It's like linear algebra with coding or something.
Yeah, it's like a topping, like a pizza topping.
Yeah,
you want coding,
you want whatever, you want sausage or not, And some people are like, I don't know how to code, I don't know. But some people are like, yeah, because that really will bring it to life for a lot of students. It's like writing the code, it's kind of, I talk about building the tools. You once you write the code to do stuff, it's like you just kind of mentally, at least for me, I sort of mentally own it, cognitively own it. I'm like, yep, I got it now. I totally get it. I can see the solution in my head now. But one thing I was going to say, the Euler's method was the Euler's method topic. I kind of remember that was a real problem early days, right? We had a really low pass rate on that, and that took some effort, didn't it? To get
it took
right?
some effort. Yeah, it stands out as being one of the topics I found that was quite hard to teach in like an online in our settings. We just didn't. I can't remember. It's quite a long time ago now, so I can't quite remember the efforts. But I remember we tried sort of teaching it, as you might find in regular textbooks. That didn't work exactly, so we iterated on it, still didn't work. I think it took sort of 3 or 4 goes, and in the end we came up with like this really sort of sleek, simple notation, a kind of like a tabular approach, which kind of avoids a lot of indexes. I think I call it index hell when there's just unnecessarily indexed, Y, I, J, all that kind of stuff. You want to avoid all that as much as you possibly can because it's just cognitive load. Wait, what does that index mean? Was that index? This approach, the approach we settled on, avoids all of that stuff, and so we're just going to carry that through to these other methods. There's other things you can do too, like to sort of help build intuition. So before we even start with Euler's method, we get them to kind of like do like a tangent line approximation, by hand, so they kind of visualize, okay, this is what we're actually doing.
This is what we're actually.
Yeah. And then you formalize it in the form of Euler's method. And then once you've got that down, it's like, okay, well, now we can improve Euler's method because Euler's method kind of sucks. So,
Mike, when I taught it in the BC calculus course, my kids, they hate that. They hated Euler's method. They're like, because you make the big table and it's boring. It's annoying.
Yeah.
I mean, it's a computational process. Yeah. It's supposed to be done with a computer, not really a human hand.
Yeah, true.
I mean, unless you're there in the 1800s and you're like, well, this is the best I can do.
Yeah. But you really need to do those competitions, as painful as they are, you really need to do them so they get under your skin. So when you actually come to code something like that, you know exactly what's going on. It's very easy to sort of look at a formula, create like a Python script, which is like 30 lines long. It kind of gives you an answer. It's like, well, don't really know what's going on here. It's exactly the same mentality we've got with this machine learning course. It's like, we want people to do gradient descent by hand, so it really gets under their skin. So when they actually translate that into like a coding environment, they know exactly what's going on.
It's going to get under their skin in more ways than one. And one of them, they're like, I ain't doing that. But then they will know it. It's like, dude, like now you know it. I know you didn't love it, but now you've mastered it. You intuition through repetition.
Yeah, I mean, it's one of those things. I mean, like, when it comes to things like gradient descent, I mean, we were talking earlier on in the show about, people that sort of like they kind of like went started the top down method of becoming machine learning engineers and never really did the bottom up part. So they kind of vaguely know what gradient descent is, but not really. And it's like that's not a good position to be in if you really want to make kind of like cutting edge technology or pushing the boundary on things. So yes, it is a necessary evil to kind of to go through those painful calculations by hand.
Got to get inside the trade, as you say, Jason.
That's right. It's such a you earn your beans. That's where it's like you learn, you develop that intuition, and then you can the abstractions stuff all fall into place. But if you try and skip the concrete examples, skip the repetitions, and go straight to the abstraction formulas, you're just like cargo cult math. You're just parroting stuff. You sound
like the buzzwordy.
You sound like you know what you're talking about. Yeah. Oh yeah, blah. It's like okay, they're like they can't really solve anything.
The nice thing about some of these numerical methods is that even the more complicated ones like RK4, is like they are actually extremely intuitive if you actually spend the time to get the notation right, to get the examples right. So yeah, they've got every opportunity for it to get under their skin to the point where they know it really well, without necessarily completely hoarding over the coals.
Yeah. Well, I'm excited. Well, I think it's going to be, I'm sure it'll be top notch, and I'm excited to see it as it come together.